Okay. Hello. So I hope you guys had an opportunity to write the Unit 1 exam, whether in person or online. I uploaded the entire exam and the answer key with a couple of hints on the Google Classroom, and in this video I'll be going over the full solutions to all 8 questions of the exam. So let's start with number 1. It asks us to evaluate this following limit. Now, we haven't gone over this specific type of limit, this specific form, right? But it's easy enough to modify, right? So we've talked a lot about in previous lessons multiplying or dividing on both the numerator or denominator to get what we want. So for this one, I think a good idea to start would be getting rid of all the denominators. So multiplying x cubed to both the numerator and the denominator would get you limit x goes to 1 of x cubed minus 1 over x minus 1. And this is a very straightforward limit. Use the difference of cubes to factor the numerator. So x minus 1 times x squared plus x plus 1 divided by x minus 1. And the denominator, you can cancel these out and plug in 1 to get 3. So 3 would be your answer for number 1. Pretty simple enough, I think. Number 2, function f of x is continuous and positive. Okay, on the set of all real numbers. So we're given continuity and positive. Keep those in mind, right? If limit x goes to 1, f of x equals 6 minus f of 1 squared, then what is the value of f of 1? Now, by the definition of continuity, right, the limit as x goes to 1 has to equal the function value itself, since we're solving for f of 1, right? So we can rewrite this as f of 1 equals 6 minus f of 1 squared, and f of 1 squared plus f of 1 minus 6 equals 0, and this is just a quadratic equation, right? So 3 and negative 2, so f of 1 equals negative 3, or 2. But we have to remember that f of x must be positive, so the correct answer would be 2. Okay, so that was number 2. Moving on to number 3, we are given that x fx plus 6 over 2 x fx as x goes to infinity is 2, and we're asked to find the following limit. Now, as you can see, x fx is repeated 3 times, but in the denominator of the final thing that we're trying to get, we don't have the x in front of it, so we might have to think about that. But first, let's take a look at our given limit, and I think we can simplify it, right, so x fx over 2x fx is just 1/2, so we can pull the 1/2 out, plus, and then 6 over 2x fx is 3 over x times f of x, and that has to go to 2. So we can find the limit as x goes to infinity of x times f of x, right? So 2 minus 1/2 equals 3 over 2, so 3 over 2, that has to equal 2. Now, here's where things might get tricky if you're not familiar with limits, right? We know that x times f of x goes to 2, but do we know what f of x goes to? Now, if you remember, in our limits unit, we said there were 7 types of indeterminate forms. So the first one was 0 over 0, we had infinity over infinity, we had infinity minus infinity, we had infinity times 0, and then infinity to the power of 0, and then 1 to the power of infinity, and 0 to the power of 0. If you look at this limit and notice that x and f of x are multiplying each other, and when x goes to infinity, then this will go to infinity, right? So it's an infinity times something, but the limit exists as a real number, right? It's a real number. So f of x has no choice but to go to 0 because we have to make that 0 times infinity indeterminate form. Okay, so this is the key part in recognizing that f of x must go to 0 when x goes to infinity. So our limit becomes 0 plus 2, and then our x f of x goes to 2, so it's 2 plus 4, and that's 6 over 2. So the final answer is 3 for number 3. Okay, so that was numbers 1, 2, 3. I think if you were familiar with indeterminate forms, right, you would have been able to solve this one quite easily too. All right, so let's move on to number 4. So number 4, we have a piecewise function defined for us as x minus 1/2 when x is less than 0, and negative x squared plus 3 when x is greater or equal to 0. And we're given that the function f of x plus k squared has to be continuous on the set of all real numbers. Okay, so there's a couple things that we have to realize here. Remember that all polynomial functions are continuous on their on the set of all real numbers, and for piecewise functions, right, the point that we need to focus on is the boundary, right? So the boundary between 0 would be a place, a potential place of discontinuity, but everywhere else it's just a polynomial plus a constant squared. So everywhere else it's going to be okay. So the only point we need to look at is when x approaches 0. Now the left-hand limit, if we go 0 minus, right? 0 minus, we're going to get negative 1/2 as our left-hand limit, right? So our function is going to be negative 1/2 plus k squared. And at 0 plus and the function value itself, so 0 and 0 plus, it's going to be what? If we plug in 0, it's going to be positive 3. So 3 plus k squared will be our function value and the right-hand limit. Now, in order for the function to be continuous, these two have to be equal to each other, right? So equal. Now there's two outcomes, right? So x squared equals y squared, you have to square root both sides, but either one of them might flip a sign or they might not flip signs. If both of them flip their signs, then it's the same thing as not flipping a sign, right? So there's two outcomes, right? Number one, the signs don't flip. Negative 1/2 plus k equals 3 plus k, and we immediately get like a contradiction, right? Negative 1/2 equals 3, so this doesn't work. So one of them has to flip their sign. So in the second case here, we're going to say that, let's say negative 1/2 plus k equals negative 3 minus k. So 2k equals negative 3 plus 1/2, so that's negative 5 over 2. So therefore, k has to equal negative 5 over 4, and that would be your answer. Okay? All right, so basic continuity, right? Number 5, I think around this point it starts to get a little bit more interesting. So let's take a look at number 5. Right, so we're given a limit and we're given two unknowns, right? So this would be one of those questions where you have to go back and get more pieces of information out of it. And our limit looks like this: x to the power 4 plus 4x, and then minus x to the power 4 plus x. Okay, and that has to equal 6. It says to find the value of a plus b. Now, if you look at this limit, right, the first thing we do is to plug in, and when we plug in, the numerator goes to infinity, but the denominator is an infinity minus infinity indeterminate by itself, right? So this is, we haven't covered this explicitly before, but now we have to think, right? So it's an infinity minus infinity in the denominator, and I'm not sure if it's going to, if the limit will exist or not exist. Now, what we've been doing with all of our radical limits is to rationalize whatever part has the radicals in it, right? So since we can't immediately analyze what's going on, it will be a good idea to rationalize. So let's go ahead and rationalize it. So this squared minus this squared is going to be 3x, and then the numerator is going to be ax to the power of b times square root of x to the 4 plus 4x plus square root of x to the 4 plus x. And you can see that we can cancel out the x, limit x goes to infinity of a over 3 times x to the b minus 1 times x to the 4 plus 4x plus square root of x to the 4 plus x. Okay, now I think we got a slightly more better picture, right? As x goes to infinity, this part goes to infinity, right? And as x goes to infinity, we don't really know what x to b minus 1 goes to because the unknown is in the exponent, right? If this is positive, then this will go to infinity. But if it's negative, if the exponent is negative, it will become like that, right? If the exponent is negative, this will go down to the denominator, and then this whole thing will go to 0. But we kind of need that, right? Because we know that the limit is 6, meaning that the limit exists. Therefore, this has to go to 0, right? This has to go to 0, which means that b minus 1 has to be a negative number. Okay, well, then we need to consider the degree, the apparent degree of this this bracket right here. It's square root of x to the 4, so the degree is 2. Now, if this degree was negative 2, then the degrees would equal each other, so we can use the a over 3. But let's imagine that this degree here was like negative 10. If this was negative 10, then the denominator would blow up, and this whole thing would go to 0. That means that everything here, since they're all multiplied by each other, would go to 0. And we can't have that, right? Because the end limit has to be 6. It's a real number, but it's not 0. Therefore, this degree has to be locked in at negative 2. Because we have to make use of the a over 3. If this degree is less than negative 2, or greater than, if it's less than negative 2, this entire thing will go to 0. If it's greater than negative 2, then the numerator would win, and this would go to infinity, right? So this degree has to be negative 2, and that has to be b minus 1. So b has to equal negative 1, right? So this is the kind of thinking that you have to do in your exam, right? So comparing, remember for infinity over infinity limits, we always compare the degree of the numerator to the denominator, right? So we're doing that process here. Okay, so b equals negative 1, but we have to find the value of a, so we have to go back. And if we look here, we can take the constant term out. X goes to infinity, and then b is negative 1, so it goes down to x squared, and then the numerator is x to the 4 plus 4x plus x to the 4 plus x, and this has to equal 6. Now, the degree is 2, so we compare the leading coefficients. 1 plus 1 over 1 is 2, so 2a over 3 has to be 6. Therefore, a has to be 9, right? Okay, so b equals negative 1, a equals 9. We got all our unknowns. So therefore, a plus b has to equal 8, and that would be your answer. Right, so plug it in. Since we have radicals, we rationalized. And then the important part was comparing the degree, right? What happens if the degree is lower than negative 2? What happens if the degree is higher than negative 2? So we got our b value from the degree. We went back to the limit to find the value of a. So I think this is a really good problem of getting various pieces of information out of a single given limit. Okay, number 6, I think we can solve it over here. So we're given this function. So we have negative 2, and then this is negative 2 comma 2. We have an open hole here, closed hole here, and then this goes down to negative 2. And then we have 1, and then it goes up to 2. We have 1 comma 2, like that, and then we have an open normal here. The function is defined here, and then we go down to 2. And then it's defined here like that. Okay, so we have this function. This is f of x. And what we're trying to find is limit x goes to -2 plus of f of x, so composite functions, and then plus f of limit x goes to 1 minus of f of x. Okay, so for the first term, we've done composite limits of composite functions before. So what we need to look at is when x goes to -2 plus, so it's going this way, what does the y value, what does f of x approach? It approaches 2, but it approaches 2 from the bottom, right? So f of x is going to 2 minus. So we go to 2 minus, and as we go to 2 minus, we get to 0, right? So it's a two-step process. The first term would be 0. Now the next term, notice how the limit symbol is inside the function, right? So this is not the limit of a composite function anymore. This whole thing, this limit, remember, this is a number, right? A limit, if it exists, is a real number. So what we're doing is we're doing limit x goes to 1 minus. So 1 minus would be 2 in this case, and we're simply plugging in 2 to get f of 2, right? So f of 2 equals 1, and 0 plus 1 equals 1. That's it, right? You can sort of eyeball it. But remember, the position of the limit symbol changes the meaning of this expression, right? Here, it's just a function value. Here, it's a limit of a composite function. So just differentiating between those two. Okay, and we get to number 7. Now, you might have noticed that the difficulty ramps up quite a bit. And this is a very interesting problem to look at for a couple of reasons. So for number 7, we have f of x equals x squared plus 6x plus 12. So we're given a quadratic, and we have an integer k. So k is in the set of integers, and it satisfies the following condition. For all real numbers k. So remember, if we, from a couple classes ago, this means for all possible values of t, the value of limit x goes to t of x squared over f of x squared minus kx plus 2 f of x exists. And that's it, right? Find the sum of the minimum and maximum possible values for f of k. So in the end, we need to get a range of our integer k and then find the minimum and maximum value of this function. So what we're trying to find, right, is the minimum and the sum of the minimum and maximum possible values. So maybe it's usually a good idea to notice what you're trying to find, right? In order to do that, we need to sort of get an understanding of what this parabola looks like, right? So the axis is -2 under 6, right? So that's -3. So our parabola is -3. And if you look at the discriminant, if you use the simplified discriminant, it's 9 minus 12. So that's less than 0, right? So it's an important thing. Maybe it will become important later on. Discriminant is less than 0, so this parabola is floating above the x-axis. So that's what we know about f of x. And now we turn to the this scary-looking limit here. Now, for all real numbers t, it has to exist. Do we have to worry when the denominator is not 0? If the denominator is not 0, we don't have to worry about anything, because then this number will be defined, right? It's just plugging in t. The only places where the limit might not exist is when the denominator equals 0. So that should be our main focus, right? So when the denominator equals 0, we should set this equal to 0, right? You notice that we can factor out f of x, and then this becomes f of x minus k times x plus 2. And let's set that equal to 0. Now, a times b equals 0, a equals 0, or b equals 0. But notice how, since we figured out that the discriminant was less than 0, this parabola is floating on top of the x-axis. It's always going to be positive. So this term, no matter what the value of x is always going to be positive. So if it's going to ever equal 0, then this expression has to equal 0. We have to recognize that. So what we want to do, if this, we want this limit to exist for every number t that we plug in, right, is this has to never equal 0. Now, if we substitute x squared plus 6x plus 12, it's going to be x squared plus 6x minus kx plus 6 minus kx. And then this is going to be negative 2k. So plus 12 minus 2k. If we don't want this to be equaling 0 at any real number t, this is also a parabola with a positive leading coefficient, so it's going to be opening upwards, right? It's going to be concave up. So here we also want d to be less than 0, right? The discriminant to be less than 0, so that this will never touch the x-axis. Therefore, at no point it will equal 0. So let's do that. The discriminant is 6 minus k squared minus 4 times 12 minus 2k. So that's k squared, and then minus 12k plus 4k, so that's minus, plus 8k, so that's minus 4k, and then 36 minus 48 is going to be minus 12. So k squared minus 4k minus 12 is the discriminant, and we always want it to be less than 0 so that the parabola does not touch the x-axis. If we solve that, this is going to be 2 and negative 6, so k is between negative 2 and 6. Now, if you stopped here, you've done half of the problem, but you're missing a couple of cases, right? We did this so that we quote, played it safe and made sure that this was never going to equal 0. But we have to consider this, right? What if this actually equaled 0, but it was a 0 over 0 thing, and it factored out with the numerator, right? That can happen, right? So we need to verify that either this cancels out with the numerator and the limit exists after all, or we really need to prove that the limit does not exist when the denominator equals 0, right? So there's only 2 possible values of k where the denominator will equal 0. So number 1 is the denominator is always greater than 0, right? Number 2 is going to be when the denominator equals 0. So there's only 2 cases here. K equals negative 2, right? And k equals 6. Right? If you set this equal to 0, then the roots will be negative 2 and 6, right? So when k equals negative 2, we need to verify, will this exist or not? Now, if we take a look here, I think this expression is pretty nice to plug in k equals negative 2. So it's going to be x squared, and then 8x, right? Plus 8x. And then this is going to be plus 16. And then that's going to be multiplied by f of x. And this is going to be x squared. Limit x goes to t. Now, if we rewrite this, this is going to be f of x times, right, x plus 4 squared, x squared, and then limit x goes to t. Now, we can obviously see that if we plug in negative 4, right, when t equals negative 4, right, when the limit goes to negative 4, the denominator goes to 0, but the numerator does not. It's a constant, it's 16, right? So the limit does not exist. It will go off to positive infinity, right? Because this is always larger than 0, and this is always larger or equal to than 0. It will go off to positive infinity. So this doesn't work. What if we try k equals 6? Then 6 minus 6 is 0, and 12 minus 12 is 0. So we get f of x times x squared for our denominator, and our numerator is miraculously x squared. So for every x, since we know that when x goes to 0, it's not actually equaling 0. We can cross it out. And since this is always greater than 0, this satisfies the condition. Limit exists for all t. So therefore, our final range of k is going to be -2. It's going to be greater than -2, but it can be equal to 6. So this will be our final range of k. And remember, k is an integer. Now, if we go back to our parabola, it's going to be from -2 to 6. But since we do not include -2, the smallest integer is going to be -1, which is going to be over here. And our largest possible integer is going to be 6, which is going to be over here. So the sum of the minimum and maximum possible values is simply going to be f of -1 plus f of 6. If you plug in -1, it's going to be 13 minus 6, so that's 7, plus f of 6 is going to be 36, 72, and 84. So your total will be 91. So this is the answer that you will get, right? So we have to be careful, right? Even though we consider this case where the denominator is always larger than 0, right? We still have to consider when the denominator equals 0 and consider the limit individually, because stuff like this can happen, right? So the lesson that I want you guys to take out of this problem is that even though the limit looks scary, the limit, it always exists when the denominator is not 0. Therefore, the only thing you need to focus on really for this problem is, hey, how do I make sure that this is not 0? And when it does equal 0, how can I make sure that the limit will exist or not? Right? So we need to verify those cases as well. All right, so that was number 7. I think it was a pretty good challenge for you guys. And let's get to the final problem, which is number 8. Now, number 8 is probably one of the hardest problems that I saw for the past couple of years. So it is definitely a very challenging problem, but it's a very rewarding problem as well. And you can get a lot out of continuity, and especially for this one, visual reasoning. You probably do not want to use pure algebra to solve this question, because that would make your brain explode. You'll see what I mean. By drawing out what our graph looks like, we can easily identify visual features, and we can adjust our problem-solving strategy based on what we see. All right, so we have a three-piece function. So absolute value x plus 3 minus 1, x minus 10, and absolute value x minus 9 minus 1. And this is for x is less than a, x is greater than a but less than b, and x is greater than b. And we're given that a and b are natural numbers. So a, b are natural numbers. And we're also given that a is less than b and b is less than 8. So they're distinct natural numbers that are less than 8. We are given a positive number k, where f of k is negative. Okay, we need to make sure that these conditions are met when we're solving. And we have one condition. We have one condition and we have 3 unknowns. This is how powerful continuity can be. Function, it says f of k times f of x minus k is continuous on the set of all real numbers. And that's it. Find the value of f of a times f of b times f of k. So we basically need to find the exact values for a, b, and k so we can actually plug them into our function. So one major condition on continuity, and that's all we have. Okay, so what we want to do here is, first of all, we want to sort of visualize what f of x will look like, right? Because absolute values, and like if you're trying to solve this with algebra only, you're going to get a massive headache and you'll spend so much time grappling with the absolute values. So let's take a step back and visualize what these graphs actually look like. So if you look here, absolute value of x plus 3. Remember that absolute value functions look like you take whatever is below the x-axis and you flip it up, right? So if this is y equals x plus 3, then the absolute value of that is going to be this, right? You flip up whatever's below the x-axis. And then you take the whole thing, you translate it down by 1. So what you're going to get is you're going to get a V shape like that, right? So this is going to be -3, and this is going to be -4 and -2, right? Because the slope is going to be +1 and -1. Okay, we have x minus 10, and that's pretty straightforward, right? This is going to be -10, and this is going to be 10. And absolute value of x minus 9 minus 1. You see when this comes out as positive, then it's going to be x minus 10, so it will overlap with this one. But since this is 9, our final graph will look like this. And this is going to be 8, and it's going to be a V shape like this, but it will overlap with our x minus 10 for this portion. Okay, so this is the graphs that we are dealing with. Obviously, it's going to be piecewise, so we have to split it with a, b. But this is what it looks like, right? The intersection here, you can take advantage of geometry a little bit. This is what a right equilateral triangle, because these product of these slopes is -1, so you just need to find the midpoint of -2 and 8, which is 3, right? Okay, so you got this. Now we need to figure out where we're going to split it, right? Because a and b are natural numbers where a is less than b. Now, natural numbers means that the first cut is going to happen to the right of the y-axis, right? So the first cut is going to happen somewhere along here, I don't know. And the second cut is going to happen before 8, so before this dips down. So what we can do is we can draw the approximate but accurate shape of f of x. So here's our giant x-axis, and here's -1. Our graph is going to go like this, right? It's going to curve like that. We are certain that this portion will be above 0 because it's going to split for the first time to the right of the x-axis. And x is less than a, so there's going to be an open hole here. And then we jump down to x minus 10. Not to scale, but the shape is accurate, right? So we have a parallel line of slope 1. And what do we notice? 8. The b has to be less than 8. So the second cut will definitely happen below 0. So let's do this. Let's lower this a little bit more. And then it's going to go up like that. It's going to happen below -1, right? It's going to happen below -1. So, you know what? I'll go down a little bit more. And then a parallel line. It's going to cut below -1, and then it will spring back up. It's less than 8, so I know that this portion is going to be above 0. It's going to spring back to somewhere above 0 here, and then it's going to continue the V shape. So this is what f of x will ultimately look like in the end. Okay, so if we relabel our numbers quickly, this is 10, 9, 8. This is going to be b and a. We don't know that yet. This is -2, -3, and -4. Okay, so now that we've got our shape of f of x, we need to consider this, right? F of x plus k, So f of x plus k is a translation of this exact graph to the left by k, but since we know that k is positive, it's going to be a translation to the left, right? We know that. Now, we have to get back to our very important condition on continuity. As you can obviously see, there are two discontinuous points on f of x, right? And when we translate this to the left by k, the shape is going to remain the same, right? So we'll also have two discontinuous points on the graph of f of x plus k. So in total, we have 4 possible discontinuous points, yet we have to make everything continuous everywhere, right? So that's the challenge that we have to get through. How can we slide this over so that every possible discontinuous point becomes continuous? Now, if you've solved the workbook problems, I emphasized that there were like 2 main solutions for 2 multiplying functions, right? If there's a possible discontinuous point. Number 1 is send it to 0. Send one of them to 0, and even if one of them is going to be discontinuous, everything is multiplying by 0, it will be continuous with 0. Number 2, arrange it so that the left-hand limit and the right-hand limit, they have the same value when they are multiplied, right? So that's more of a finicky thing to do. So if we look here, there are 4 points where this function equals 0. -4, -2, 8, and 10. And we're sliding this to the left and we're multiplying, right? So the simplest possible case, I think, is when these 2 zeros, right? When these 2 zeros slide over here, and when these 2 zeros, when these 2 discontinuous points slide over exactly to -4 and 2. Does that make sense? So this slides over here, making these 2 discontinuous points continuous, and these 2 discontinuous points slide over to -4 and 2, making it making all 4 points continuous. So let's try that idea, right? That's going to be our simplest solution, and to denote that, I'm going to draw some, extend some of my dotted lines so that we can visualize what's going on. Okay. So what we're doing here is 8 goes to A, 10 goes to B, right? Like that. And A goes to -4, and B goes to -2. So that's our first case. Okay? Remember, everything is shifted to the left by k. So this is going to be k, and this is also going to be k. Now, this is -2, and this is 10, so k equals 6. Right? K equals 6, then 10 minus 6 is 4, B equals 4, and 8 minus 6 is 2, A equals 2. Let's think about that. What we need to verify is that f of k has to be negative. So if we take a look here, this is 4, right? This is 2, and this is 8. So 6 has to be between 4 and 8. And all the function values between 4 and 8 are positive, right? So f of k is positive, which means that we violated that condition, and unfortunately, this doesn't work out. Okay, so our simplest case of making them all zeros turns out doesn't work by this problem. So then we have to carefully consider what we're going to do next. The other case that I said is, if something does not go to 0, then you need to match the left-hand limit and the right-hand limit so that their products equal each other. The only way that we can do that is when B slides over to A, right? If B doesn't slide over to A, it's never going to get canceled out, right? It's always going to be discontinuous. So our remaining cases we'll be thinking about when this happens, when B slides over to A. Okay? So should I draw a horizontal line here to differentiate our cases? B slides over to A, so this point is covered. Yet we still have to think about this discontinuous point, right? Because if we slide this over like that, this is still going to be discontinuous for in our f of x, right? Sorry. this is supposed to be x, right? F of x times f of x plus k. Okay, so b slides over to a, and one of these has to slide over to b. So which one, right? And where does a have to slide over to? So right now what we're doing is b slides over to a has to slide over to one of these zeros, right? And one of these two zeros has to slide over to b to cover that discontinuity. Okay, so what's going to happen here? Let's say that, should we take the two inside values first? If 8 slides over to b and a slides over to 2, right? Then we get this kind of picture, right? We get the length of k here, here, and here. So 3k, so in this case, 3k has to equal, what is it? The distance between 8 and negative 2 is 10. 3k equals 10, so k equals 10 over 3. It is a positive constant. But notice that a and b are natural numbers, right? The distance between two natural numbers is always a natural number, but the distance is k, and it's not a natural number. So this can't work, right? So you can't pick these two inner numbers. So what if we take, what if we take the outer number, 10? 10 goes over to b. Let's say that 10 slides over to b, b slides over to a, and where can a slide over to? Now, we've learned our lesson, right? If a slides over to negative 4, then 3k will be 14, and k would be 14 over 3, which is not a natural number, right? It's still, k has to be a natural number because it's the distance between a and b. So we can't go over to negative 4, but we certainly can go over to negative 2, right? Because the distance between 10 and negative 2 is 12. So 12 divided by the 3 k's is 4, right? So 3k equals 12, k equals 4. And now what's our value of b? b equals 6, and a equals 6 minus 4 is 2. So we got that one case. And our final case to consider, right, is when k still slides over here, right? We have 8 sliding over to b and a sliding over to negative 4. It's still 12, except that our numbers are different, right? This is k, and a slides over to negative 4. This is also k, right? Then this would also be k equals 4. But this would be b equals 8 minus 4, right? 8 minus 4 equals 4, and 4 minus 4 equals 0. So now that we have these two final cases to consider, which one works? Well, first we should check if the fk is less than 0, right? K is 4, k is 4 in this case. Let's see here. In case number 3, f of k, so it's 2 and 6. So 4 is definitely below 0. So f of k works for this one. And here, a is 0, b is 4, and k is 4. So f of 4 1, 2, 3, right? F of 4 is what? Positive, right? F of 4 is positive because we're guaranteed that, remember, since we set this up, this point is always above 0. Aha, so this also doesn't work, right? So in the end, we've only got this case remaining, right? because we wanted k to be a natural number, and everything else has to click, right? So for our final verification, right, if you're not sure on time, it will probably be a good idea to make sure that when B slides over to A, the left and right hand limits match. So let's do that for our final verification. So limit, so B slides over to A, and A was 2, right? Limit x goes to 2 minus of f of x times f of x plus k. And k was what? 4, right? Equals, that's just f of 2. Let's see here. Limit x goes to 2 minus of f of x is going to be on this function, right? It's going to be on the first function. So it's going to be 2 plus 3 minus 1 times, that's 4, right? And then f of x plus 4, as x goes to 2 minus, it's going to be what? 6 minus, right? 6 minus. B equals 6, so that's 6 minus. We have to look at this value. What's 6 minus 10? Negative 4, right? So that has to be 16. Let's check our function value. F of 2 times f of 6 equals, f of 2 is negative 8, right? We have to look at this value, which corresponds to this middle function. Negative 8 times f of 6 is this. So we have to look at the third graph. 6 minus 9 is negative 3. 3 minus 1 is 2. So this matches negative 16. We're looking good. And finally, the positive limit. Limit x goes to 2 of f of x plus 4. As x goes to 2 plus. So 2 plus, we have to look at this, which is the same as the function value, which is negative 8. And then here is going to be 6 plus, right? 6 plus is going to be here, which is the same as the function value 2. So that equals negative 16. They all match as, whoops, negative 16, right? They all match as negative 16, which means we found the correct case. K equals 4, A equals 2, B equals 6. So we found our 3 variables by analyzing continuity. So therefore, our final calculation is f of A. Now f of A is, we calculated that as negative 8, right? Negative 8 times f of B, remember we calculated that as 2. Now what's f of k? K is 4, so it's in between, so we have to look at this guy. So 4 minus 10 is negative 6. So therefore, negative 8 times 2 times negative 6 would be positive 96. And that is your final answer for number 8. Now, yeah, this is probably one of the most challenging problems that I saw based on pure continuity, right? But notice what we did, right? Visual reasoning allows us to get rid of our incorrect cases way more quicker than if we had used algebra from the very beginning, right? Drawing out our absolute value graphs and knowing that, for instance, this is always above 0. This is always above 0. This portion will always be less than negative 1. Those kinds of visual cues really helped us to analyze our cases, right? And remember, for 2 multiplying functions, there are 2 major ways of getting rid of discontinuities. Either multiply something by 0 or get a perfect match of the left and right hand limits like we did here. And bringing all of that together, we get like this very amazing problem, I think. Yeah, this is really good. All right, so I hope you, wherever you are, whatever level you're at, managed to find some problems that challenge your abilities. And I hope you learn some things out of it, right? How to treat problems, how to approach them, when to use specific facts and foundational skills, right? There was nothing that we haven't learned about any of the problems that are here today. But it takes a lot of practice and grit to apply the basic things that you learned to complex and to situations that you haven't seen before, right? So I hope that was a really overall positive experience for you guys. Okay, so next class we'll be starting Unit 2. This is where things really start to get fun, right? We've built our base on limits and continuity, and for the next class we'll get started on differentiation, all right? All right, thank you for watching, and I'll see you in the next one.